Hi, good morning, or good afternoon, I should say. So I'm going to carry on from where I left off in the recorded lecture, but first there's a chance for anybody to ask anything if they like, or send a message through on chat. Please do just speak up. Okay. Well, if there's nothing there, I'm going to continue talking about our propositional calculus, our kind of formal deductive system that we were outlining. I finished up last time. I talked a little bit about the axioms that were there in the earlier part, mentioned in the first part of the course. And we want to now talk about what we can do with those axioms, what we can find from them, what we can prove from them. So let me, I just realized, excuse me a moment. So let me recap a little bit once more about those. So this is pages 44, 45 of the notes here. I'll switch on my camera for this here. So what did we see here? We had a collection of axioms for our deductive system here. And then there were two rules of inference. This is called either modus ponens, which basically says if you've got P and Q and R, and if you've got P and you've got P implies Q, sorry, P and Q. If you've got P and you've got P implies Q, then you can deduce Q here. If you've got a formula which you've proven, phi, then you're allowed to immediately deduce for all vk phi. There's two ways of assembling a proof. You can look back on previous lines and generalize an earlier line, or you can use modus ponens on two previous lines. So it's very simple, two particular rules. And then a proof, I said, was going to, somebody's unmuted. A proof then is going to be then a finite list. And everything on the proof either comes from a set of hypotheses, gamma, or it comes from earlier, or it can be an axiom from one of the axioms on the list, or it comes from earlier things by using one of the rules. And that's what this is here. And I made the observations, of course, if you can prove phi from gamma, you can prove phi from any superset of gamma. And in fact, what happens in a proof is you only use finitely many hypotheses of gamma here. So actually only finitely much of gamma is used. Right? So this observation will be useful later. Because a proof is very much a finite object, right? It's something that one can, it may be very long, we may not be able to see the beginning from the end, but in theory, it's a finite string of lines in our language. So, so what actually we're going to do is just look a little bit at how proofs function, right? And there are a lot of examples and lemmas here of how this proof system works. And actually, to save time, right, because of the way the lectures have panned out, I'm actually going to skip most of them. But for completeness' sake, I've left them there, or I put them there in the notes for you. And we won't be doing a lot of details of how this proof system works, right? But I just want to get some of the features of it over. And then we're going to skip forward to sort of something like page 70 or so, and start doing something slightly different. But I do want to, in this lecture, just give some idea of how this proof system works. So let's look at the bottom of that page 45 here. So here's a very simple example of a proof. I've got gamma, it has just got one formula in it, right? And I specified that V1 is not one of its free variables. So this is what a proof looks like. It's only got 4 lines. What I've got here is an instance of A1. So what I mean by that is I've used as one of the axioms, I've quoted an axiom here using phi and psi and phi, which actually happens to be the variable letters I used when I wrote the axiom out. I then quote the hypothesis from gamma, phi here. So now I can use modus ponens on the 2 lines above, right? I've got phi and I've got phi errors something. So I apply R1, rule modus ponens, and I get the consequent here. So from these two, I deduce this. And now I apply rule 2 here. So rule 2 was generalization, and there was this caveat that I can't put a quantifier there if it's quantifying a free variable from my hypotheses. And that's why I had this specification here. So what we've got then is a proof from phi of this here. So we would write something like this. So from gamma, I could write phi here. I prove this thing. And actually, to just save clutter, if it's just a single sentence, we just kind of skip the brackets around it here. So I deduce this from this. Right? Okay, assuming that V1 wasn't the free variable of phi, and psi was anything whatsoever. Right? So I'd say that this is deducible from phi within predicate calculus, right, here. And my little remark 316 above just says, well, of course, if there was something else in gamma, some chi here, it's entirely relevant. We didn't call upon chi in this proof. So the presence of chi in gamma was not relevant here. Okay. Any questions there about what that simple example shows us? Okay, let's move on then. So again, I'm now going to go forward to these pages 60 to 70, and I'm just going to say something about on a few things that are on pages 61, 62 here. Okay, so here's the first thing. So the lemma here, which we could prove if we were going to delve into this further, which says the axioms are all universally valid. So our axiom set here, to say that an axiom is universally valid means it's going to be true in all structures, no matter what assignment function, no matter what assignments we make to the free variables. And one would reason about this by saying, well, this and this and this, these are all examples of tautologies. So these are just true just by looking at truth tables, no matter what the truth or falsity of phi, psi, and chi are. These will always come out because on every line of the truth table for this formula, one ends up with a t in the final column. Likewise for these two here. Skipping ahead to A6, this is an equation. It just says VI equals VI. And whatever structure we pick, this will always be true in that structure. So this is a universally valid formula here. Here I've got two things. If these come out to be equal in a structure, then it won't matter whether I substitute T0 or T1 into a formula here. Let's look with our usual caveats about whether these things are properly substitutable. If these turn out to be the same in the structure, whether this is true or false will be the same whether I put in T or T1 in the second place here. So I could reason about all of these things here and argue that they're going to be true in every structure under every possible assignment. It needs to take just a little bit more reasoning here. So I'm just going to assume, right, that we know that the axioms are universally valid. So that's a property that we'll take of our axiom system here. So you should underline that and make sure you understand what that means. So 358 here. This is, I mean, I put this here as much as anything. Well, it gives us another example of a proof, but it also shows us how awkward actually the system is. Just think of this very simple statement here. P arrows P, phi arrows phi. And any reasonable proof system, you ought to be able to prove something like this, right? No matter what the phi is. But actually, it's rather hard to get to that stage, get to derive phi arrow because phi. I mean, it takes 5 lines to do it, using rather long lines, axiom instances. So what I've got here is an instance of axiom A2, right, at the very beginning. So again, to go back to A2, here it is. Actually, it's an instance of A2 where I put phi for both psi and chi all the way through. So this here, right, is just A2 with phi's put everywhere for psi and chi. Now axiom A1 here, the instance I've got here, axiom A1, I've substituted phi arrows phi for psi itself. And here it is, phi arrows phi for psi. So I call this an instance of A1. And now if I have done this right, I'm going to apply modus ponens to these two previous lines. Here, this is my antecedent. Have I got this right? Instance of A1. I think I've looks like I've messed it up. I want to deduce this one here. I don't want this to be here. Okay, so this is phi. Okay, sorry. So I kind of, yeah, this shouldn't be here. And I don't need this bracket. And this instance of A1 that I've got here is just simply, I've just put phi here for psi. Previously I said phi arrows phi. It's just phi. It's here. So phi arrows phi. And the point is that this here is, if I think of this as P arrows Q, this is P here. And here's Q. And now I use this instance of A1 again, right? The same one as above. Okay, I can repeat the use of a hypothesis. That's no problem. So now I've got here, this is then the antecedent of this. So I can do a P and a P arrows Q, a modus ponens here, and deduce this Q. So phew, I've got there at the end, right? I struggled a bit, but I've now deduced this from no hypotheses at all. I've just used axioms, right? So I conclude this is phi is a theorem then in predicate calculus. So this is, so, you know, a little bit of ingenuity is needed, and even to just deduce very simple formulae. Yeah. Right? So, you know, you'd be crazy to try and do mathematics in this Hilbert style system, right? But that actually isn't the point. The point of the Hilbert style system is that what you've got is something that's very simply described. It's just a small number of axioms. There's just two rules of inference. So you can then, you know, just apply mathematics to this very simple system, right? I could have, I mean, if this was a course perhaps done in a philosophy department, or you would have a much more natural kind of deduction system. You would have a deduction system where you had rules that looked more like everyday reasoning rules and axioms or rules of proof, not just these two. You'd have many more different rules of proof, again, which would kind of mirror to a better extent the kind of reasoning we do in everyday life. But we need to prove these mathematical theorems about the system. So then it's best to have a simpler system as possible, right, to actually do those theorems about the system. But it means that working within the system, you know, if we were foolhardy enough to do that, would then be very complicated. So nevertheless, we have to prove certain basic things in the system, right? Like as I've just done, and I'll show you some more later, right? But once we've done those, we can kind of sort of forget about them, right? As long as we can quote them. And that's what I'm going to be doing later on in the course. So what one rapidly does is to try and find some ways of speeding up proofs, right? Making things a bit more slick, right? And this is what the deduction theorem does. So the deduction theorem says, right, if I've got a set of hypotheses, gamma, and I've got another hypothesis, phi, then from that gamma union phi, those hypotheses here, if I can deduce psi in the system, then actually from gamma I can deduce phi arrows psi, which is a different formula. Right? So see what it says. So I've got gamma and I've got phi and psi in the language. And I'm going to use hypotheses over here, gamma phi. So gamma phi here, I mean, formally we would write something like gamma phi psi, like this. But as I said before, we want to reduce clutter, so we just get rid of these here. So this is gamma union singleton set phi. So the deduction theorem says, okay, if I can make a proof, a finite list of formulae, which constitutes a proof, using these things from here as hypotheses, then from gamma alone, I can prove this implication, phi arrows psi. And you can see here, there is actually something to do here. Just because I can deduce this symbol string, psi, using these as hypotheses, doesn't necessarily mean I can prove this symbol string just from gamma alone. But any reasonable system, one ought to be able to do this. After all, if we kind of step back and think about what's happening here, this is saying I can prove psi from these hypotheses. Okay, well, that ought to be the case if the system is any good, that from hypotheses gamma, I can prove if phi is well, then psi. So it's entirely sensible to want something like this. So indeed, the theorem here is kind of verification that we've got a simple system. And we're not going to do the proof, but let me just say, roughly how it goes. Suppose from gamma and phi I can prove psi. So what does that mean? That means I've got a list. I've got a proof like this. Sorry, this is psi. It's a finite list here. Everything in here is either an axiom, or it comes from gamma, or it's phi, or it comes from earlier lines by one of the two rules of proof. And it ends up with the desired result, psi, here. So this would be a witness to the truth of this, right? If it's been formed correctly, if it's a correct proof. I mean, I noticed, and I will come back to that, checking whether something is a correct proof is an algorithmic procedure. All you have to do is check that you follow the rules correctly for building a proof. If I can check whether something is an instance of a tautology by some algorithm, and if I can check whether something is in gamma by an algorithm, I can check whether something is phi, I can check whether this string has come from two earlier strings by a correct application of modus ponens, and so on. So everything here is entirely mechanical. If you were to kind of program this, given a program for telling you whether something is in gamma or not, you could put all these programs together as subunits and just create a program to check whether this is a correct proof from gamma with phi. Okay, so that's an aside. It's entirely, mechanically checkable. But we want to prove, the deduction theorem says, okay, we want to show this. So actually you do what would probably come to you naturally if you thought about this long enough. What we do is we take this proof here and we just show that I can always write by induction on this index down here, I prove this. Until I get down to phi r is phi n, which is psi. And we show that we can prove each of these just from gamma by itself. So It's an induction on the length of the proof. On n, the length of the proof. Gamma phi psi. Where we show for I less than n that gamma phi arrows phi I. Yeah. And when I equals n, it's just what we want here. So it's kind of a natural, right? Yeah. Okay, that's all I want to say about the deduction theorem here. Let's just look at some examples, some lemmas here. We just see that they're saying sensible things. You probably realize, of course, if you've got a statement, if you say for every x and for every y, something happens, it's exactly the same as saying for every y and for every x, something happens. So that was talking about interpreting a formula, what it might mean. Well, we can prove this symbol string. Right? Now I've got the deduction theorem. I can start out with this here as a hypothesis. And maybe I can work my way through to this here. So what I've proven here is this. So those few lines that I've got here, those 7 lines here, right, are showing this. Now that I've got the deduction theorem, so I can now just say by the deduction theorem, I've got this. So this is an outright theorem from no hypotheses here. And the lines in between show you how you get from here to here, from A to B. Sorry, can I read what the last page said? Sorry, is this here that you're asking about? Sorry, my writing is not so good here. So it's an induction on n, the length of the proof. The proof being gamma comma phi going through to psi, where we show for an I less than n that gamma proves phi arrows phi I. Okay, I hope that's all right. Okay, all right. Now there are many kind of rules that you can derive, rather like the deduction theorem. I'm not going to go into many of these, but let's just see what they're saying. It's called the Particularization Rule. So this is saying if you have a hypothesis that phi holds for all v0s, then in particular, it holds for any particular term that I could substitute in for v0. Right? So this is entirely unobjectionable. Right? If it holds for everything, it holds for a particular t. So as long as I can keep to the syntactic rules for substituting a term in for this variable, then I can derive it. I can derive this symbol string in my system for v0. And here is its proof. I take this as a hypothesis. I then see that this actually is an instance of axiom A4. In fact, this is exactly what I want. Right? So I apply modus ponens to these two, and I deduce this. So I've got this here. There's a slightly more complicated E rule or existential rule, which is sort of a, well, not exactly a converse, but it says if I've got a term I can substitute in for the formula, whenever this is true in a structure, I'd like this to be true in the structure. And it would be, because the interpretation of the term is the thing that makes phi true. So there does indeed exist something that makes phi true. So with each of these formulae that we can prove, or these relationships of provability, if we think about what they're going to mean, they should be unexceptionable. But we're saying here that we can actually derive this symbol string from this symbol string using the rules of proof. Here. And this is how one would do it here, which I shan't go into. There's one feature here that I've used to speed it up, which has been crept in. I've used an instance of a tautology rather than of an axiom. So this is, you might think, is kind of cheating. But actually, I can prove that everything that looks like a tautology is provable in the system. So I could prove something like this from no hypotheses at all. But by doing it like this, I've kind of just said, okay, I'm going to tacitly, I know that all tautologies are theorems. I'm just going to quote a theorem right here. So I'm quoting something we've already proven. So in here, I could substitute a proof of this thing. But again, to speed things up, I just say, oh, it's an instance of a tautology. Right? Here. And what is it an instance of? It's an instance of, here I've got P or psi arrows not chi arrows, and here I've got chi arrows not psi. So it's a contrapositive rule here that I've got. Substituting chi for not chi. So it's just a contrapositive rule. So formally, when we're developing proofs, we're allowed to, we expand what we're allowed to do, and we allow ourselves to quote tautologies because of this theorem here. And on the next page, you can see a proof of this. Right? I mean, if you're interested in, you're welcome to read this, but you can see it's quite lengthy. Right? And we're going to skip it. So it goes down page 64. And the next few lemmas and corollaries just kind of build up a library of different rules and results. These kind of simple results that are here. So this is a corollary to the E rule. Right? If phi is true of everything, then phi is true of something. Down here on 364, this is a big long list of just kind of things that are true of kind of propositions, right? It's nothing really to do with quantifiers. You can't see any quantifiers occurring down in here. It's just saying, I can derive phi from not phi. From phi and psi and not phi, I can prove psi. So again, if it's not the case that phi arrows psi, then not psi. That perhaps needs a bit more thinking about. If I've got phi arrows psi and I've got psi arrows phi, then I can prove phi arrows psi and psi arrows phi, which is the same as phi is equivalent to psi here. Proof by contradiction. Suppose from gamma, I assume not phi. And suppose from not that, I can deduce both psi and not psi. Then this not phi is a contradictory assumption. So from gamma alone, I can prove phi. It's like one of those arguments, Assume for a contradiction not phi, and then we deduce from that two opposites. So our conclusion is phi. This is something you could think of as proof by cases. Very similar to the proof, well, almost exactly like the proof by contradiction above, right? I've just taken away the and. If I've got two different proofs, one of psi and another proof of not psi, then I can prove not phi from gamma. So again, this is something about what you can do within the system. I can produce this symbol string from this, right? Knowing that there are proofs of these two kinds. So each time what's implicit in here is a conclusion which we've derived using the rules of the system. Okay. Anything else to say here? Yes, perhaps here is something to, this phrase will come back. Yeah. I say phi and psi are provably equivalent. Means I can prove psi from phi, and I can prove psi from phi from psi. So by the deduction theorem, I know that phi arrows psi is provable. And from this, I know that psi arrows phi is provable. So it's a short step from knowing these two to saying, okay, phi is equivalent to psi. Again, remember that what this says here is phi arrows psi and psi arrows phi. So this double arrow is just an abbreviation for this here. But this is saying something, right? This isn't trivial. This is saying I've got a proof of this symbol string, and I've got a proof of this symbol string. Then there's yet a third proof of this symbol string, which may not be immediately connected to these two proofs. And you can see that here it is occurring down here in this lemma. If they're provably equivalent, then we can prove this here. And the proof of B here tells you how to do it. Right. this, I mean, this will not occur very much, if at all. And the idea is that if I take phi and I replace some of the occurrences of psi in chi, I end up with chi prime. So chi prime is the tweaking of chi, where I've replaced in the formula psi, some of the in chi, I've replaced some of the occurrences of psi by phi. And the idea is, at least in the lemma, right, is that, I mean, if I've got two provably equivalent things, and I change pieces of chi by replacing one by the other, I end up with something provably equivalent to what I started with. So again, the proofs are down here about those symbol strings, right? But you don't have to look at these here. And maybe I don't say so much about these here. You can see there's lots of them. Yeah. So this is saying, you know, it's like that for all distributes over and. Right? These are logically equivalent. These are provably equivalent, these two things here. Notice here there's a single arrow. This is if there is something such that phi holds and psi holds. Right? Indeed, that implies there is something that phi holds and there is something that psi holds. But not necessarily conversely. It may be that there are different things that make phi hold and psi hold. So it doesn't mean that I can reverse the arrow and say that this implies there's one thing that works for both. And that's why this is only a single implication here. Similar concerns for the line above. Right? So again, a host of different theorems of predicate calculus about these different formulae. Okay? And proofs of some of them are there on that page, 67. And so it goes on here. Some proofs involving equations down here. Right? I can prove this. Well, I better be able to prove something like this if I'm going to be able to deal with equations. I better be able to prove this as well. And it shows how to do it. But in themselves, the proofs are not interesting, really. This is something that I'll quote this one later on. That's why it's here now. Right? And it, by itself, it's just a bit mysterious. Why is this here? It's just saying that right? I've got a completely new variable here. It doesn't occur in phi. So it says, well, whatever v0 is, right, phi holding is equivalent to saying there is something that's v0, right? And phi holds of v1 substituted in for v0. So this looks kind of a little bit kind of peculiar by itself here. And this one says just the same thing, well, with for all. So the idea is, here's for all v0, so maybe phi's got v0 in it, right? So this is saying, well, if phi v0 holds, then whatever I pick, if it equals v0, then phi will hold with, well, v0, v1 substituted for v0. So I may just quote these. I can't remember which one of these it is that I want. Perhaps later on here. Okay, so someone asks, are the bits that I skip examinable? No, the bits that I skip are not examinable. What I'm going to do towards the end is produce a comprehensive list of pages, lemmas, and things that can be omitted. Right? I mean, of course, you know, if you look at some of the past old exams, they will say, produce a short proof of one of these formulae, of the kind that I've just been going fast over here. Right? I don't think we're going to do that because I want to save time and skip some of the mechanics here of this proof system. But I do want to be able to refer back to something like the deduction theorem. Right? That was why I spent some time talking about that. So you may need to look back at some of the lemmas that are stated here. I'm going to refer back to one of these two. I don't remember which one it is, right? Because this is, you know, in a full course when we did all of it, when we do all of these proofs, you know, we'll have proven this. But so I keep the proof here, but we're not going to go through it. I'm going to skip it here. Okay. Fine, that takes us up to the end. We'll come back to that remark later in the course here. So what we'll do next time is move on to the next section here, the soundness and completeness.